the part which is bad here is at most like 5 fraction of the volume of P. Okay, so there might be some bad edges, but we can control how many of them. And the hope is that maybe, okay, if we still say that we want to work on GU, G prime, we now know that, okay, there is some F that is good for many parts, but there are some still small bad parts. So maybe if we just continue working on on U prime, maybe and try to reuse information about F, maybe we can make some progress. Because at least the bad part is small. Make sense? Or
what if the S part also have again inward flow?
say it again.
The part which we have to cut, the S part, that also can have inward flow.
This.
The flow in the wrong direction.
So most of the part is good. Most of the cut edges here will be good. Like, first of all, like the part here will go, the flow will send in the correct direction for sure because it's outside P. There is no excess here, right? And we said that if H is big enough, then the black part, which is bad, like the higher H is, the black part, the smaller the black part. So I'm not sure I understand your question.
So I was just asking why can't the flow go inward in S as well, but I understood because
By S you mean P?
No, there's an extra part as where we are planning to cut.
What part? I mean, we find a cut, and we just plan to cut this thing out and try to work in U prime. That's the plan. And my point is that this F here is at least like quite good for a lot of boundary edges of U prime. So maybe if we try to reuse F, maybe it's good. Okay. Yeah, and that's exactly what we are gonna do. So we will try to like iterate. So we start with empty flow, like and trivial level, and U1 is just U, and set H to be something like this, and start with the time T1. So what we can do is that this is U, and this is battery. Yeah. We try to solve this flow problem, right? And know that I give F and L as an input too, but initially it's just empty. And in the beginning, well, if you solve this flow problem and there is no excess, you're done again. Yeah. But if there is excess, then you get some cut. Get some cut P, call it P1. So P1 will be such that, like before, like most of the flow out of P is like they are almost saturated, except some small part. So because H is big, H is said to be this big, so like the part which is not saturated is like a 5 fraction of this, which is just, if I remove this 2/5 here, then you get this. But anyway, the part which is not saturated is small. That's the only thing you need to think about. And now what we do, we just cut P out of U. Now work with U2. U2 is the remaining part. And you define F and L, F2, L2, to be just F1, L1, where you restrict yourself from this graph, G1, GU1 to GU2. Okay. By restriction, like you can really define it in a natural way, right? Each of the edge, F here, if it is inside here, it just remain the same. But the only thing you need to think a bit more about is this boundary edge. Well, so let's basically. So let's draw things carefully. If this is U, this is P, and if this is an edge, then when you work with a U2, this is U1, this is U2. If the flow is such that this is 10, then what you do is that when you work with U2 with a boundary edge of U2, then this guy become like a boundary vertex of this edge, right? So you just set the flow from this boundary edge to this guy to be 10. Like it's just a natural way to restrict things into the subset. Okay. So yeah. So now once you restrict F and L into the subset, then just try to call the flow. Try to call the same flow problem on the new U. If you find another cut, well, cut it and repeat. You cut it, restrict the flow and label into the new graph and repeat. Okay. But note that the F and L that you have found from the first iteration, you feed this thing as a valid input to the next iteration, as a valid state to the next iteration. So that's important. We kind of reuse information from the previous iteration and feed it into the push relabel algorithm. So that's a very important feature of push relabel. Like as long as you just feed some valid state to it, it just can continue running from there. Yeah. Is the algorithm clear? The description of the algorithm. Okay. So you need to show that, like, we just need to verify that, like, every time that we do this restriction, we get a valid state for the new graph. So like, what really happened, right? Like, so when you run a push reliable, you have some level of vertices. What are we doing here is just phi p, so, and cut things out. And the remaining part here, like, is just new f and new label. But this new f and new label should be valid inside the new set. But like, this is almost immediate, just because any edge that skip level would still be saturated. So the first condition is checked, and any node that have level more than 1 would be fully absorbed, like, because like nothing really changed here. So yeah, the valid state is still valid. Like, after restriction, you still get a valid state. So you indeed you can really just continue running the algorithm. Okay. So now we have that. You can see that we will just stop whenever, like, as long as there is some excess and you get some cut, you just cut and keep pruning. And when you stop, you have that, you get a flow on UT, and the flow is feasible. So you know that whenever you stop, UT is an expander. G induced by UT is an expander. So you know that like, at least one condition is done. Like, when you stop, GUT is an expander, you're good. You just need to, what we need to show is just that the prune part, the total thing that you prune out is not too big. That's the only thing we need to say, right? Okay. And why is that the case? So to show this, we will, like, let me tell you an intuition first. First of all, the first set that you prune is going to be small, right? That we know, because the first set, maybe I draw things. The first set that you prune is at most, the volume is at most initial excess because they are fully absorbed. But what is actually happening after before the second round, you can see that we actually add some new flow, new mass into the system. Where do we add? Well, so along this cut, there are like a lot of edges that is already saturated, but there are some small number of edges that is not saturated, or even in the wrong direction. But for each of these guys, we said that we define a new flow problem on top of the new set, and we said that we want to send flow along this guy. So for each of this bad guy, we add a new mass to kind of inject this guy so that it goes in the right direction, right? So that's like the amount of mass that we add into the system is just proportion to the to the part that is non-saturated. But we design it in such a way that they are small enough. How much small is this small? And this small is like smaller than the volume of the Prun set, and smaller by like a lot of like 1/50 factor, or in like you can make this thing like a 1/1000 or anything. But the point is that this is the amount of mass that you might need to add before the second round begin. But okay, we actually add some new mass into the system. But note that when you do that, you actually delete this thing from the system. So amount of mass that is destroyed from the system is the volume of P. P1. So you add 1/50 mass into the system, but you delete this much. So it means that the total mass that you ever add into the system is like at most twice from the initial mass, right? Imagine that like you have some process such that whenever you add something new, you delete two things. The total thing that you ever add, that you have ever seen, is going to be like twice the initial thing. So now think like if we add 1 unit of thing here, we actually destroy 50 units of things. So the total mass that we ever add is like twice what we have initially. Now, with this in mind, you can say that, the total of mass that we ever add into this is like twice the initial mass. But now, the total size of the Prun set, every time that you find a Prun set, this part is fully absorbed by the sum mass, which means that the total volume of the Prun set is at most the total amount of mass that you have ever seen. So question? Like, is this statement like I didn't make it very formal here. I think what does it mean by like a new amount of mass that we add? Why exactly is like this? Should I try to explain more about this, or do you think is fine?
Could you show how this interacts with like the valueness of t plus 1?
Why?
This should have some interaction with the new flow.
Right. The question is, okay, yes. Like, you mean when I say like intuitively, when I said I add some mass into the system, does it affect validity of S and of F and L? Is that the question, or?
Maybe even because this delta UT and TUT are just defined like with regard
to the new set.
some constant mass, like 2 over 5 degree. Then
Not sure if I understand.
it's just about, I guess it's notion of new amount of mass can be just really calculated from something in the previous iteration.
Yeah. It is really like from the. It should actually. Yeah. So this, like, it's really like this. Like, let's say that this is a cut. This is your before you cut, right? And if you cut, if this is your PT, yeah. Then there are a lot of things that already like fully saturated out of P, and there are like some part which is maybe not fully saturated or even go in the wrong direction. So what we do is that first of all we restrict ourselves, like we really now delete this thing out, and we want to define, like we kind of define a new flow where this is for each of these guys. We just say that okay, it send flow in the same direction. Yeah. And for this guy, like by the way, if this is saturated and like if this is like already 2 over 5, and if you set that the source of this new battery edge is 2 over 5 too, then it's like we don't add anything into the system. Like even if you say that this is amount of source, there are some flow that go out of this already. So no new mass. But for this guy, we still set this guy, the source of this guy, to be 2 over 5. But the amount of mass out of this guy actually is negative. It actually like go into, so the total mass that we add into this thing can be like 4 over 5. Yeah. So just so that first of all it cancels the thing that come in, and it should push back to, yeah. So actually, right, yeah. So this is why and this thing is really like actually 1 sec. Yeah, this whole thing, like maybe we should think of this as like a sum over all node in the battery of UT plus 1. And this is just 2 over 5 minus the flow out of U in this. Yeah. And most of this thing is going to be 0, but some of them can be as big as 4 over 5. Make sense? Yeah. Okay. So you see that, yeah, we really like the total thing that we prune is small. And why is that? Because we design the algorithm in such a way that whenever we cut something out, we destroy a lot of mass, and we add not too many mass. So the total mass in the system is small, and the total prune volume is at most the volume of the initial mass. So we are good. So that proved the correctness. Except that you see here, like we say it like we call this thing might be many times. Why is it the case that the total running time of this is small?
Because every time we are only inserting less amount of volume, we'll finally end up like exponentially decreasing.
Yeah. So yeah, very good. So if you consider the algorithm for the local algorithm, right? Everything that we can do for local algorithm really can be charged to the mass that we add into the system, and we say that each of the mass in the system is charged h time. So that's why the total running time that we said before is the total mass times h. All the work we can charge to the mass. Each unit of mass, you charge h to it. But now we just say that okay, it's true that we run this thing many calls, but it doesn't matter. All the thing that we do is that we keep adding some mass into the system, and every cost that we do, we can still charge into the system to the mass, but the total mass we add is still small. So total mass that we add in the system is at most 2 times this thing in the initially, and the total time is still h times this thing. Yeah. So this is hand wavy. I will put into the note to make it formal. But you see that the great thing about push reliable is that it's just so flexible. Like you have some you run the algorithm up to some point. You even cut some graph out of it, and say that if the remaining part is still valid, you can just continue running. And you just, you add some mass into the system. Now, just say that, you can continue running. But the total time is just charged to the mass. So, yeah, when we talk about a Ford-Fulkerson or blocking flow, this thing doesn't really it's very hard to think about it. You run the algorithm up to some point, you delete some part of the graph, or you add some new source, so it's hard. But this thing is flexible and easy to think about. Yeah, so the total time is going to be just this times h, which is what? Which is d over phi log n.
So we can have pruning more parts from the graph. If the exchange with better time complexity.
Can we prune more so that we get faster algorithm, you ask, or?
Just for this algorithm, we graph, right?
So
So adding mass to this system.
yes. Sorry, I'm not sure I get the question. Like we keep pruning until like at some iteration, you get a feasible flow with no excess. When that happens, you stop, right?
So the final P is larger than the.
Yeah, the final P is just a union of all P you find. But the final P is still small. It's at most the total mass that you add. Okay. Question?
Here we set H to be log n over 5n, n is getting smaller, but H is like log volume over 5n, volume is getting larger. So is there any other way to set this H?
So the whole goal of setting H, like all you need is that H should be large enough so that this thing is constant factor below the volume of P. If we don't do that, then I don't know how to bound the total mass in the system, right? But once you have that, if H is big enough, and then you will get this thing is like a constant factor times P, like let's say 1/2. That's enough. Then the total mass is small. Yeah, but so if H is smaller than log n over 5, I'm not sure how to get this bound. Oh yeah, that's true. Yeah, that's true.
Yeah, so since n is getting smaller, but the volume is getting larger during the iteration.
Right. I think if it's safe to set H to be log of the total mass times 3 over 5, or maybe with maybe some constant here. This should work. I just need to do the math, I think. Yeah. Okay.
In this case, delta of V is just the boundary edges which we are introducing.
Yeah.
Because of deletion, right?
Boundary edges times 2 over 5.
Yeah, boundary.
Yeah, right.
So it's much smaller than N, right?
Yeah, much smaller. Yeah. Yeah, but it's like in the log still. So it's saving, but just still saving something inside the log. Yeah. All right. More question? Otherwise, we will be done. Okay, so next week is gonna be about like trying to so I talk about this so that I can teach you expanded pruning, because I just show some slide that say that from expanded pruning you get everything in dynamic algorithm. So it's good to know this technique. Although, okay, from next week, like we have only 2 weeks left, I will tell you how to get